All right, so here we are. We're ready to do our calculations. What I've done is I've taken our list and I've put it into my calculator for each different region. If you want to do this with me on your calculator, you can pause and put them in. I'm just going to keep going. What we're going to do is use our calculator to grab a lot of the information that we need from the calculations. So what I'll do first, let's see here. I took some of this, I erased, I know I had the Muse written under here, and I slid this over to give me some room to write. But the things that I need to grab from the calculator would be X bar, the sum of the X's. I need to know the variation and the sample size. Sample size, I don't need my calculator to do that. That's just 3. So what I'm going to do is I'll go stat, calculate, one variable statistics, and I'm going to do list 1. X bar is 28 2/3, so I'll write around that 28.7. The sum of the X's is 86. That's just all of those added together. Our variance. Now recall with our calculator, it gives us the standard deviation, not the variance. Here's the sample standard deviation. We want the variance, so we need to square that. I'll just grab this calculator to do that quick. 5.0332222957 squared. And I get 25 1/3. We'll write that as 25.3. Now we called this our first list, our first sample, so I'm going to put ones by all those, so I remember that's what those are. Now we can do the second list, and this will be our X bar 2, sum of the X's for 2, variance for the second one, and sample size for the second one, that's 4. So I'll just go back to my calculator. I'll go stat, calculate, one variable statistics. Now I'll change it to list 2. And we'll write these down. So 41.25. Sum of the X's was 165. Our variance, well, our standard deviation is 5.123475383. So when I square that, I get 26.25. Let's call that, we'll just say that's 26.3. Okay, I have 2 more regions to do. I'm going to pause my video and do these so you guys don't have to watch me do it. And then I'll start back up when I'm ready. All right, so this is what I got for our third and fourth samples for the south and the west. Okay, now we're ready to start grooving here. So first thing we need to find is the grand mean. That's the X with the double bar. Now how do we find the grand mean again? It's the sum of all the X's divided by the sum of the sample sizes. Now when we take a look at this, our big N, what was our total sample? 3, 4, 3, and 4. That's 10, that's what, 14? It's 14. Now, what we have to do for the numerator is add all the X's from all the lists together. Now, we've already done that for each list, so instead of adding all those together, I can take the 86, the 165, the 99, and the 111, and add those together. 86 plus 165 plus 99 plus 111, 461. So we have 461 over 14. So our grand mean is about 32.9. All right, what are we going to calculate next? The sum of the squares between. Now, take a look at what this is telling us to do again. We need to take, for each sample, the sample size times the sample mean minus the grand mean. So this is the difference between the sample mean and the grand mean squared. And then we need to add that up for each sample. So for our first sample, sample size is 3. Sample mean, 28.7. So we're going to take 3 times 28.7 minus the grand mean 32.9 squared. That's for the first sample. Now we have to add this up for each sample. There's i's here, and that just is for the different sample 1, sample 2, sample 3, sample 4. So now we're going to do that for the next. Sample size 4. The x bar for this sample is 41.25. So we're going to say plus 4 times 41.25 minus 32.9 squared. So the difference between the sample mean and the grand mean squared. Now we'll go to the next one. Sample size was 3. Sample mean was 33. Plus one more, the last one, 4, sample mean 27.25. I'm running out of room. I was writing too big. Squared. Can't lose our squared. Okay, that's what we needed to add up for the sum of the squares between. And now, just got to figure out what that is. Yeah, I definitely could have spaced this a little bit better. So the sum of the squares between, I'll just do that calculation. What I'll do is I'll set up all of them and then I'll pause and then I'll use my calculator to find out what they are. Now we need the sum of the squares within. Sum of the squares within, we take each sample size minus 1 times the variance. So 3 minus 1 times 25.3. Plus, we're going to do this for each sample. 4 minus 1 times 26.3. Plus, I know that was 3. 3 minus 1 times 37. Plus, I know the last one had a size 4. 4 minus 1 times 52.9. This had a much larger variance than the rest of them. All right, what I'm going to do is I'm going to pause my video. I'm going to grab my calculator. I'm going to find those, and then we'll resume. All right, so this is what I got for the sum of the squares between, 459.3, and the sum of the squares within, 362.2. All right, what's next in our calculations? Now we can find the mean square between by taking the sum of the squares between over our degrees of freedom for our numerator. And we haven't written what those are down yet. Degrees of freedom for the numerator. How do we calculate that again? It's the number of samples minus 1. Number of samples is 4. 4 minus 1 is 3. There's the degrees of freedom for the numerator. How about the degrees of freedom for the denominator? Degrees of freedom for the denominator is the total sum of the sample sizes minus the number of samples. So our big N we found was 14 minus our number of samples is 4, which is 10. So recall that the mean squares between is the sum of the squares between 459.3. Oh, I got my decimal in the wrong spot. Over degrees of freedom from the numerator, right? Degrees of freedom from the numerator, which is 3. And it gives us 153.2. All right, mean of the squares within. Mean of the squares within is the sum of the squares within divided by the degrees of freedom of the denominator. That's going to be 362.2 divided by 10. So 36.2. All right, that's kind of intensive for all the calculations, but we're good. Finally, we can find our test statistic, which is, going back, mean of the squares between over mean of the squares within. So that is 153.2 over 36.2, which is 4.231. All right, there's our test statistic. Now, let's set up our F distribution. We know where that is. Let's set our rejection region. So how do we set our rejection region? Well, recall that we have a 5% level of significance, and we know our degrees of freedom for the numerator denominator. Now, one thing I should mention that I haven't so far is that this is always going to be a right tail test. Okay? It's always going to end up being a right tail test for us. If the means of the squares between is really close to the mean of squares within, it's going to be about 1. If it's bigger like we have, it's to the right. So we're going to head to the back of the book to our F distributions. I'm going to pick the table with a level of significance of 0.05. There it is. This is on page A23. Degrees of freedom for the numerator are just 3. Degrees of freedom for the denominator are 10. So I'm going to scoot this down. And I see 3.71. So our test statistic is 3.71. So let's say that's right there. Sets our rejection region. Where is our test statistic? Okay, it's to the right of that, isn't it? Okay, so what does that mean for us? It means we reject the null hypothesis. And what was the null hypothesis? The null hypothesis is that all the means are the same. So we're rejecting that. And when we look at that, we see some variation here. These three are pretty close. This one's significantly larger. Now we also had to consider the variances. This had a really large variance, but there is enough of a difference. Okay, I would suspect that that's the one that's different, right? Now we would have to do a 2-sample test to try to identify a little bit more closely on that this is really the one that's different. We could do sample 1 and sample 3 and see if those are different or not. 1 and 4, see if those are different. 3 and 4, see if those are different. And if none of those are different, then this one would have had to have been. Okay, so what is our conclusion? At least one of the means is different. So we are supporting the analyst's claim that there is a difference in the means. There is enough evidence to support the claim that not all sales regions have the same monthly mean. There we go. I think we have an idea which one it is, but we can't say that exactly from our test, but they are definitely not all the same. All right, so there's our first ANOVA test. I hope you can run with this. Thanks for watching.